comparative analysis of BGP anomaly detection and robustness algorithm. I'm kind of looking forward to seeing this one because being in the routing data business a little bit, it's always interesting to see new ways to use that data to make the network more robust. So with that, I'll hand it to you.
Thank you, Dave. Good morning. My name is Sriram. This is joint work with my colleagues at NIST. So the primary focus here is to see what sort of benefit we can derive from registry data as well as the trace data from route views and RIPE arrays to make BGP robust. So there are algorithms already proposed which make use of registry data as well as trace data to do exactly that sort of thing. So we're going to review those briefly and look at some new, some enhancements to those. And I'll also present some interesting results based on data analysis, hopefully interesting. This paper was presented in a preliminary form earlier at NANOG 43 in June. Relative to that, this presentation covers more detailed, and it presents a more detailed analysis with extensive data from the global IRRs, RIRs, RADB, and RIPE arrays. Several significant additional insights have also been developed since then, and a full paper based on this work is available at the link shown on this slide. So as I said, we will quickly look at the known robustness schemes based on these types of approaches, and then we will look at evaluation of those algorithms both qualitatively and quantitatively. We'll present a number of numerical results and then present some conclusions and possibilities for future work. The Nemesis is well known. It was published a few years ago. It was presented in NANOG as well. It's based on registry data. So it takes prefix origin pairs from the updates and checks for consistency with the prefix or inetnum, ortnum, and route objects in the RIRs and IRRs. And how it does the consistency is to try to match organization, maintainer, email, etc. And if these alerts check out okay, then it's fine. Otherwise, if they fail, then an alert is generated, and they look for full or partial consistency checks. I'll explain more details of this as we move on, get further into the talk. The FAS prefix hijack alert system is based on history data or trace data. It looks for origin AS set changes. If the AS seems to be new relative to what's been associated with the prefix up until now. It looks for any new subprefix, if any new subprefix added to the set of subprefixes already observed, and it looks for last hop AS set changes. So based on those, it generates alerts. PGBGP is also based on trace data. Here, the idea is that you take observed prefix origin pairs based on update history as well as RIB entries over the last, say, 10 days. And an update or a prefix is considered suspicious if the origin AS is new relative to what's been observed in history. And even then, even if it appears new, the update would continue to get propagated, although with a local lower local pref. Sorry. If it is a new subprefix, then it is always considered suspicious and quarantined. So this is an older version of PGBGP. We'll also look at a newer version. The quarantine lasts for a suspicious period of, say, 24 hours. And during that time, if it is not withdrawn, then the update or the subprefix update is propagated. So it was pointed out that if you did that, then during events of like prefix hijack, when the legitimate owner tries to recover traffic by announcing subprefixes of their own prefix, then their subprefix updates will also be blocked or quarantined. And then this was a presentation at NANOG in 2006. And the response was that, yes, we should look into that. And they indeed went ahead and modified PGBGP so that if the AS announces subprefixes of its own prefixes, in order to gain traffic back during a hijack, those subprefixes, PGBGP will not interfere with those subprefixes. Still, there are some weaknesses that persist in PGBGP which can be improved upon. It has a short span of the historical view, about 10 days, because of which it may miss out some of the announcements from the past. For example, if a prefix owner is multi-homed and switches over from the primary path to the backup once in a while during failures or other events, then the PGBGP, because of the 10-day history, may miss out on those types of announcements. It wouldn't have it in its record. And when the multi-homing related AS origin changes happen, then PGBGP would typically unnecessarily lower the local pref. And also there are other weaknesses. For example, if a malicious user is observing a prefix being withdrawn, and immediately following that, he announces a malicious path with a different origin AS, PGBGP would not be able to detect that. It would be effectively a false negative. And also, if the legitimate owner sometimes announces subprefixes in conjunction with multi-homing related AS origin changes, then also PGBGP would quarantine the announcement unnecessarily. Now, how do you mitigate this? There are two ways. One is to try and increase the historical view, the span of the historical view. So we consider making it 6 months instead of 10 days. And the other way is to take advantage of registry data to whatever extent it can help. So the two can possibly complement each other and perform better. So that is where the idea of an integrated approach comes in. You can also call it a hybrid approach, which makes use of both registry data and history data. So rather than go through this system diagram at a high level, I will get into some details so you can appreciate how it can be implemented to work. So on the registry side, we have INET nums, routes, and OTnums, for example, in RIPE. And there are similarly net handle and other objects in the ARIN registry. In RIPE, we also have a maintainer object, and the RPSS, the security protocol that goes with RPSL, makes use of like authentication based on the maintainer object. So we tried, kind of based on that fact, we try to do this consistency checks between route object and the corresponding INET num and OTnum. So essentially, we try to match the maintained by, the org ID, the maintained lower, etc. If those match, then we call it consistent. Otherwise, we would call it inconsistent. Okay. So based on that consistency and inconsistency definition, what we do is we take, first of all, you can do an analysis of the registry by itself, where we can take the route objects, the prefix origins from the route objects, and match them with the corresponding OTnum and the INET num, and look for consistency as we defined on the previous slide. And in this process, we would also look for a super prefix. If the prefix itself does not seem to have a corresponding INET num or OTnum, rather a corresponding prefix, we would look for a super prefix. If a super prefix has a INET num, in which case we would do consistency check with the super prefix INET num. So basically here we try to establish if the route object appears to be consistent with the INET num and OTnum registrations. And based on that, we can generate scores for the registry in itself without any tie-in with the historical data at this point. So by doing this, we can see what percentage of routes in the IRR are consistent with either the INET num or the OT num or both. Okay. So having done that analysis, then we can get into actual BGP robustness, where the BGP algorithm the BGP protocol can make use of the registry data to validate an update or invalidate it. The way that is done in the registry-based algorithm, here only the registry information is being used. You have the update stream, and the updates are bringing in prefix origins, and our intent here is to try to validate that origin. And what we do here is we feed in the prefix origin into this algorithm, and we check whether a route object exists. If it does, then we check if that particular route object is consistent with its corresponding INET num and OT num. And based on that, we can generate these different types of outcomes where we say there is no route registration, or there is full consistency, meaning that the route object exists and it is also consistent with the INET num and OT num. Or we can say that there is partial consistency, in which case only the prefix or the origin AS are consistent. They check, but not both. And not consistent means that it's not the route object exists, but is not consistent with either the INET num or the OT num. Now we go into the history-based algorithms. This is an enhancement of PGBGP here. So we have a trace data start date and a trace data end date. That is our history period. We choose 6 months in our analysis. And during this time, we see the prefix origin advertisements and the prefix withdrawals. And we see like what is the maximum duration of time it stayed on in the RIBs persistently. And it may have come and gone multiple times, but we pick that duration which is maximum, where it persistently stayed in the RIB. And if that happens to be greater than 48 hours, we call it stable. If it is less than 48 hours, we call it unstable, meaning that this prefix origin seems to be transient. And we can add to that to make it a hybrid algorithm. And here we have an enhanced hybrid algorithm, where we have the same history algorithm as I described on the previous slide. And now we bring in the registry data. We take 2 snapshots of the registry data from a date right around the start date of the, we take a date right around the start date of the trace data, and another date for the registry from close to the end of the trace data. So we have 2 registry snapshots because that way we'll be able to capture any registrations that may have occurred during the history period. And so now we have this hybrid approach, where if in some cases the history shows it unstable, but the registry shows that there is full consistency or partial consistency, then we can trust that prefix origin and actually call it valid rather than suspicious. Now we look at the evaluation. So here there are a couple of tables. Basically, this lists the checks and questions performed by the different algorithms: the registry-based, the trace data-based, PGBGP, the enhanced trace data-based, and the enhanced hybrid. And these differ in the type of checks or questions they ask regarding the validity of prefix origin. And registry data, as you see, is based on primarily doing registry checks, the kind that we have mentioned. PGBGP is based on looking at the last 10 days and then asking questions regarding whether the prefix origin was observed in those 10 days. And the enhanced hybrid or enhanced trace data, it modifies the PGBGP to say that, okay, let's take a 6-month window and look for a 48-hour stability, and based on that, validate the prefix origins. And in all of these, what is always done is that if the prefix origin by themselves are not validated directly, then you look for a super prefix. If the super prefix with that origin can be validated based on the registry or the history, then it's fine. We would call it good rather than suspicious. And this is another list where the algorithmic features are highlighted. The green generally means good, and the red would mean bad. So here we list the types of data sets these algorithms use and also the types of situations handled by them. So it is important that, as we discussed earlier, if a legitimate owner announces a subprefix of its own, that should pass. That update should not be blocked or quarantined. So those types of situations, these algorithms should handle well. So I'll leave it for you to take a look at this table. This table follows logically from the descriptions that we have provided so far. We can move on to look at the comparative analysis of these algorithms. Now, what we have done is we have encoded registry-based, enhanced trace data-based, and the enhanced hybrid algorithms for evaluation. The enhanced trace data-based algorithm, as I have mentioned, is a variant from BGP. The algorithms are run on top of NIST terrain framework. Terrain is an acronym for something mouthful: testing and evaluation of routing robustness in assurable interdomain networking. We call it the Terrain project, and we have a database which consists of, it's a unified database of the registry and trace data, registry data for several months, over a year now, and trace data from route views as well as RIPE-RIS for up to a year is already in the database, and it's grown already to about 5 terabytes. For the purpose of this presentation, we will focus on origin AS validation, although the work can be extended for path validation in the future. The use of global RIR, IRR, RADB, and RIPE-RIS data, they were made use of in this study. Results are reported broadly for global registries as well as specifically for regional RIR and IRR registries. We used 6 months of trace data, January through June of 2007, and initialized with stable RIB entries from the beginning of that period. So basically, over that 6-month period, we are able to capture all the updates and RIB entries, and also sort them out according to whether they are stable or unstable. Then the registry data is for 2 dates, prior to and towards the end of the 6-month window. Results on comparison of algorithms follow. Thanks. Thank you. Some caveats apply. Going forward, we have not included the net handles from ARIN that Mark Koster's talked about this morning. Those are growing about 10% or so every month. These net handles contain origin information. So I'm referring to the net handles with origin information in them. They are growing at the rate of about 10-15% per month, it appears. So as that becomes more complete, we would be able to make use of them going forward. And we would also include multiple trace data collectors from route views as well as other collectors from RIPE-RIS. Here we use only RRC00 collector. And also the RPKI-based ROAS and BOAS can be included going forward. Now, the set of results that try to provide us some insights into how this data would perform for BGP origin validation. So here we are plotting prefix origin pairs according to stability and consistency scores. So on the y-axis is the prefix percentage of observed prefixes over that 6-month period. And on the left of the x-axis, you have 4 unstable cases, and on the right, you have 4 stable cases. And the 4 cases correspond to registry consistency checks, whether there is a route in the registry, that's NR, no route. NC is not consistent, PC is partially consistent, meaning the prefix or the origin are consistent, but not both. And FC is fully consistent, both prefix and origin are consistent. So what we see here is that there's a small percentage that are unstable, maybe up to 4 or 5% that are unstable in each of these cases. Whether you just focus on the RIPE prefixes or the ARIN prefixes or global, the percentage that are unstable is relatively small. So bulk of them, anywhere from 94 through 97%, seem stable historically stable. And in the case of RIPE, many of them are registered and also fully consistent or partially consistent. There are some, about 10%, that are not registered. So that's for RIPE, the green curve. The red and the blue correspond to ARIN and APNIC. There you see that there are many stable prefixes, but they are not registered. The routes are not available. So the IRR, as Mark also mentioned earlier, the IRR is incomplete, so that is the reason for that. Now, globally, the story is somewhere in between, if you look at all the prefixes globally. Then the next thing we do is the comparative performance of these three types of algorithms: registry, history, and hybrid. Here, history refers to the enhanced history, and hybrid refers to the enhanced hybrid. The solid curves are where the percentage of observed prefix pairs are classified as good. So as we go from registry to history, there is a big jump in what you consider as good, because history shows this high percentage that are stable, but registry has a certain incompleteness. And hybrid improves upon that a little bit further because it takes advantage of registry. So hybrid is, in the hybrid algorithm, the registry data complements the history data and improves upon the performance slightly. And that can be seen here in this. Here we are showing the percentage reduction in suspicious pairs. So reduction in suspicious pairs translates to reducing false positives. So the registry to history, obviously there is a big increase, big reduction. And then we go from history to hybrid. RIPE relatively performs better. It reduces the suspicious ones by another 10%. That hopefully translates into lower false positives. And then we can look at these heat maps where it is about the prefix, whether it seems to be good or bad, whether it had the potential, whether it looked like it was hijacked or not. So this is the internet map of the addresses. So these three, if you compare, so this is for the registry. It has a lot of red and green. The RIPE region relatively has more green than ARIN or APNIC or others. Then you go to the history. And in the history algorithm, you see a lot of green, a lot of red went away and was replaced with green because of prefix origins being observed as stable historically. And the hybrid algorithm gives you a slight improvement. If you flip this, there are a few more reds that turn into green as you go from history to hybrid. So the gist of it is that if we make use of the combination of registry and history algorithms, there is a possibility to increase false positives and improve the performance thereby. As the registry quality improves, there is greater chance of this data becoming more reliable. Okay, I only have a few minutes left. So one quick point I want to make is that the way the registry algorithm comes in handy is because sometimes there can be these multi-origin prefixes. Occasionally, they switch from the primary to the backup path, and that could be unstable historically. But if that prefix and origin are registered in the registry IRR, RIR, then we can based on that we can validate those updates. And this slide shows that there are about 168 of those cases in which the prefix, the origin seems unstable, but it checks out well in the registry. And I'll skip this slide in the interest of time, so I can give you some time to ask questions. It examines another subtlety or detail. So at this point, I'll let you read the conclusions. Primarily, as we improve the registry quality, the history itself does a good job. As we improve the registry quality, we have a chance to augment the two types of information and improve upon these types of algorithms. Thank you.
We have time for a few questions.
Hi, Todd Underwood, Packet Fabric. So it seems that many of the good algorithms for detecting this rely upon a certain amount of history and information. This implies a separation of the control plane and the forwarding plane that doesn't exist in most architectures, because the routers don't have any history, and the control plane is sitting inside of the same box with a lame processor and not quite enough memory and no disk as the forwarding plane. do we need to separate those effectively and basically have a server in the corner running the routers as big forwarding machines to actually implement this stuff? Or is there some strategy using current tools? People have talked about big ACLs or, weird route maps or, how do you actually implement this stuff?
Actually, the focus here is to study the algorithms. We haven't gone into studying the implementation complexities. But basic idea is that you need to have a database somewhere and offline you're looking at the history and the registry and updating the history as well as also moving forward the registry as new registry information becomes available. So you consult this database so as updates come in, if you have a way to quickly look up this database to either say, yes, it looks to be good based on the history and registry data so far, or it looks suspicious. So that's the general idea, but I'm sure there are many implementation complexities that need to be looked into and processing requirements.
Others? And thank you.
Thank you.